Okay, I just want to briefly go over number 6. I know I didn't spend any time, or I didn't spend much time on it yesterday, but number 6, we take the antiderivative, and that will give us the total number of people. And then for part B, it says set R prime of t equals to, well, part B says find the time when the rate at which people enter the auditorium is at a maximum. So you know it's going to be EVT, extreme value theorem. We want to find out when the rate is at a maximum. So we have to, R is already the rate, so we're having to do R prime equal to 0 to find the critical point. Okay, so R prime, you can quickly go through power rule to get to the derivative. You set that equal to 0, and then you can just graph this function and look for the x-intercept. It ends up being 1.3296. Now, after that, then you have EVT, you're just testing your endpoints, right? So you're testing R of 0, R of 1.362, and R of 2. They all get inserted into R of t, and you're just looking for the highest value. You're looking for the maximum. So max rate is going to be 854. This doesn't represent people. This represents people per hour. So because R of t is already a rate. Okay. And then part C, it says the total wait time in the auditorium is found by adding the time each person waits, starting at the time person enters the auditorium and ending when the concert begins. Function W models the total wait time for the people who enter the auditorium. The derivative of W is given by W prime. Find W of 2 minus W of 1, the total wait time. So if I want to find W of 2 minus W of 1, that's really involving the antiderivative of W. So because we know this is true, right? The integral from 1 to 2 of W prime is W2 minus W of 1. Then therefore, the integral from 1 to 2 of 2 minus t R of t, which is W, we can just basically make that go in the calculator. It's 387.5. So they're just asking us, this is just an indication to see if students can recognize that W2 minus W1 is just the antiderivative of W prime, right? Because we know that this is true, right? We know that the integral from A to B of lowercase f of x is equal to uppercase f of b minus f of a. Okay. So this is just a general rule for any antiderivative that you take, right? If I do the antiderivative of 1 to 2 of x squared dx, you would go through power rule, right? And x squared becomes x cubed over 3 between 1 and 2, and that's what's represented by this uppercase f of b minus f of a. So lowercase to uppercase means you're taking the antiderivative by whatever means possible, and then when you plug in your upper and lower bound, that is the process of evaluating your antiderivative. So that's what this is saying. This is saying, oh, W2 minus W1, it's basically asking you to find the antiderivative and or doing the definite interval, basically saying, okay, if I have W prime, I can just take the antiderivative, and that is what I'm going to end up with. So this is just basically saying roundabout way of saying take the antiderivative of this, which I have the function for. So W prime is this, and I just enter this in the calculator. I get 387 is my total wait time. And then part D, it says on average, how long does each person wait? Well, if you know that 387 hours is the total wait time, and that there's 980 people in the concert, then if you divide those two numbers, then you get the number. You get the number of hours per person. Right, so it's 0.77 hours, but it's really 0.77 hours per person. Okay, so on the AP exam, they love to play with this. They love to see if students understand that this is really just a notation for asking to see if you can recognize that there's a definite integral involved to produce this answer. Okay. All right, so let's go to page 7, and this is more like what your FRQ quiz will look like. Okay, so the reason that I like this type of problem is because it features a lot of different things. It allows us to kind of review a lot of different aspects of what we learned over the course of first and second semester, all in one compact FRQ. Okay, so let's read this problem here. It says let f and f prime be a differentiable function. So we know that they're both smooth curves, both f and f prime. There's no sharp turns. There's no vertical asymptotes. There's no holes. Okay. So the table gives values of f and its derivative at selected values of x. So, okay, so we're going to have to use this feature somewhere down the road. And we're given g of x. So g of x is given by sine of 3x minus e to the cosine 2x. And h of x is the antiderivative from 6 to x of j of t. Okay. And these are related. Okay, so j of t, j of x, it's just representing a different variable, but it's referring to the same information. Okay, so part A, is there a value of c between 1 and 5 such that f double prime of c is equal to -3/4? Okay, so if we're looking at this here, we don't have anything dealing with f double prime, but we do have f prime. Okay, so this is actually an application of mean value theorem. So if you go to the very back of the page, there's a formula sheet. And for this quiz and the next quiz, I will give you a formula sheet with a lot of information that's going to be helpful. Okay, but when we get to the multiple choice test, then that is going to be the one test without any formulas. Okay, so but I am going to kind of work ourselves up to this. We are going to kind of, I'm still going to provide you formula sheets for the next 2 quizzes, but you're kind of using that time to kind of commit some of these to memory. Okay. So mean value theorem says this: if a function is continuous and differentiable, there exists a number such that f prime of c equals f of b minus f of a, or b minus a. So in other words, that's saying, okay, we'll review mean value theorem a little bit more, but it's basically saying that I can guarantee a slope, okay, between the endpoints. Okay, so whatever the slope is between the endpoints, between a and b, let's say there's a slope of 1/2, then there must be a slope of 1/2 somewhere along the curve. And that's what that mean value theorem is saying. But this also applies for anything one derivative down. So I can say f double prime of c is equal to f prime of b minus f prime of a, or b minus a. I can just take everything and just drop it one derivative down. And that is an application of mean value theorem. So going back to page 7, right, I don't have anything involving f double prime, but I do have f prime. So I know this is true. Right, since f prime of c is equal to f of b minus f of a over b minus a, I can take this and make it apply for one derivative down. Okay. Now I don't take the derivative of b minus a, just the ones involving the function. So if I can show that f prime of b minus f prime of a over b minus a is equal to -3/4, then there must be a place where f double prime is equal to -3/4, somewhere along this curve. So what are our a and b values? What's the interval that we're concerned about here? From 1 to 5. Yep. So that's our a and b value. So we can just test that out. So we're just kind of testing to see if this will work out. Okay, so if this is equal to -3/4, then we know we're in the clear. We can say that by mean value theorem. There must be a place where f double prime is equal to -3/4, but we have to confirm that this is actually going to be true. Is the slope between f prime of 1 and f prime of 5 actually going to show us a second derivative value of -3/4? All right, so what's f prime of 5? So f prime of 5 is -2. And what's f prime of 1? Is 1. F prime of 1 is 1. What's that equal to? -3/4. So this is basically showing that, okay, because there is a average rate of change of -3/4, by mean value theorem, there must be an exact value of -3/4 somewhere along this f double prime or f prime graph. But basically, imagine if there was an f prime graph and f prime of 1, f prime of 5. If I find the rate of change here, there must be a place where f double prime is going to be equal to -3/4, because this is equal to -3/4. There must be a place where the exact rate of change is -3/4 as well. Okay, part B. Let k be the function defined by k of x equals f of j of x. Write an equation for the line tangent to the graph of k at x equals 2. So we recognize this, right? We've been doing this ever since August, September. What information do we need to get to the tangent line equation? Slope and points. Okay, so we want to find k of 2. So let's start there, k of 2. That's going to be our order pair. We have to go through this process here. We got to do f of j of 2. And we got to go through this process to get to our y value. So if I want to find f of j of 2, I first need to find what? Find j of 2. Okay, so j of 2, j is shown by the graph. What's j of 2 equal to? Yeah, j of 2 is equal to -1 right there. Okay. All right, so if I replace j of 2 with -1, I get f of -1. So now we can move on to the f graph. What's f of -1? 4. Yeah. F of -1 over here is 4. Okay. So we have our order pair. Our point is at 2, 4. Okay, so that's the easier part. Now we got to get to the derivative. Slope, right? Slope comes from the derivative. Now look at the setup here. If I want to find the derivative, what do I have to involve here if I want to find the derivative of k of x? Chain rule, right? So chain rule. So if you go to the back of your sheet here, chain rule says if I want to take f of g of x derivative, it's going to be outside derivative times inside derivative. So f prime of g of x. So I take the outside derivative, I keep the inside intact, and then multiply that whole thing by inside function's derivative. Okay. So here, my k of x is given as f of j of x. So if I want to find k prime, how would you represent the outsized derivative? F prime of j of x times j prime, right? Inside derivative. Right. So that is the full derivative of k prime. Now I can replace x with what? 2. I'm looking for the slope at 2, so k prime of 2. Okay, we got to go through this step by step. Okay, don't jump any steps here. What would you find first? It's like a nested process here. Let's find what information first. J of 2, right? That's the easiest part, right? Finding f prime of j of 2, that's a lot going on. Let's focus on the parts that is easier to do. Okay, so j of 2, we go to our j graph. J of 2 is equal to -1. So I'm going to rewrite this problem here. I'm just going to replace this bracket here with 1. Sorry, -1. Everybody see how I got from here to here? So this is really messy right now. At least I get it down to something that feels a little more manageable. Okay, so f prime of -1. What's f prime of -1? -3. Okay, so I have that information. J prime of 2. Okay, I don't have the J prime graph, but I do have the J graph. So what's J prime? What's it asking for us to find? Slope, right? Slope. So we don't want to say -1 here. Or sorry, J prime of 2. So J prime of 2, we got to go to 2. Yeah, so 2 is here. Okay, we don't want to say -1 here, but we want to find the slope. What's the slope of this line segment? Right, so if I pick another point on the graph, the steepness is down 2/1, right? So a slope of -2. Yeah. So all this is going to get us to the slope that we want for k prime of 2. K prime of 2 equals what? 6. So there we have it. We have information needed for us to create our tangent line equation. We have our order pair. We have our slope. Now point slope. The AP exams, they love to do chain rule problems where everything is in function form. And you have to build your derivative using function form and then insert values in. And then sometimes you're pulling information either from a table or from a graph. And you have to know when to look for order pairs, when to look for slope, how to evaluate that chain rule. So a lot going on, but this demonstrates a lot of knowledge that we've learned first semester. Okay, so now let's look at part C. Part C is asking for a similar piece of information, find the slope of the tangent line, but instead of giving us something in function notation, now it's giving us something that we are actually find the derivative of. Okay, so now we're going to be involving the derivative rules for actual functions that we've learned. All right, so same process, same concept. We just have to find the derivative a little differently rather than in function form. We're doing it actually with a function specific derivative rule. Okay, so again, we want to find order pair, we want to find slope. Let me write out the g of x function here. Let's go ahead and find the order pair first. So if I want to find order pair, I know my x value is what? Pi, so I can plug pi in for x, and let's get to our order pair. This quiz is going to be non-calculated. Okay, non-calculated. Well, hold on, let me see. Yeah, so we're going to replace pi in for x. Sorry, yeah, cosine 2 pi. So what's sine of 3 pi? Sine of 3 pi, same thing as sine of pi, right? What's sine of pi? Well, let me ask you this. What's sine of 0? Sine of 0. How about this? The order pair at pi is -1, 0. So 0, right? Sine is the y value, 0. And what's cosine of 2 pi? Okay, let's look at the order pair here. This is 2 pi or 0. Order pair here is 1, 0. What's cosine of 2 pi? 1. Right? So e to the first power is just the same thing as negative e, right? Okay. Okay, so there's my order pair. Okay. Okay, so now we want to find g prime. Before we find g prime of pi, let's find g prime of x. So what's sine's derivative? Cosine of u times u prime. So chain rule there. Okay. What's e to the u's derivative? E to the u times u prime, but there's a nested chain rule here. So e to the u is e to the cosine of 2x times cosine's derivative is negative sine. And then 2x's derivative is 2. So there's nested chain rule here. Okay, so now let's replace every x with pi. Okay, so cosine of 3 pi, same thing as cosine of pi. Cosine of pi is -1. Yeah, it's the x value. Cosine of 2 pi is 1. Yep, it's the x value. So I have e to the first power times sine of 2 pi, 0, times 2. So anything times 0 is just going to be 0. So my slope is just what? -3. All right, so I have my ordered pair, I have my slope. Let's do point slope form. Okay, so y minus negative e, that's my ordered pair, or y plus e, is equal to my slope, then x minus pi. Yes.
We had to write the line equation.
Oh, sorry. It's just asking for the slope. You're right. So I can just stop at -3. Okay, so I'm sorry, I went a little further than what's asking for, but if you were to find tangent equation, you would go this far. But I think it's good for practice purposes. We'll go one step further and we gather our slope and our order pair and do point slope form. But yeah, this problem, you're right. This problem should have just stopped here at -3. Okay, part D. Find h of 4. So let's find h of x. H of x is provided here. So if I want an h of 4, I can just replace x with what? 4, right? Okay, so let's do that. If I want to find h of 4, well, let me build h of x first, put h of x down. So I want to take the definite integral of j of t. Now, j of t is given to us as a what? As a graph. So the integral means I'm going to be finding the what under this graph, involving the area, right? The area under this graph. But if I want to read the graph, I prefer to read from left to right, but this is going from right to left. So what can I do to make it a little bit easier for me to interpret? Yep, let's flip the signs and change the bounds. So we want to figure out the region from 4 to 6. Take a look, 4 to 6. That's just this triangle here. What's the area of this triangle? Mm-hmm. 1/2 based on sight. What's the area? Yep, 1/2 2 times 3. That's 6 over 2, which is 3. So we can put a 3 in place of this. But we know that that 3 is only representing integral from 4 to 6. So h of 4 is actually what? -3. Next part is asking for h prime of 4. Before I can find h prime of 4, I should first find h prime of x, right? So here's h of x. If I want to find h prime of x, I'm just going to write out what I want to do. I want to find the derivative of this. Okay, does this remind you of anything? What's going to happen here? Cancel out, right? This is second theorem. So derivative and integral on top of the same function, that will go away. The only thing that gets replaced is this upper bound and for t. So this is just equal to what? J of x. Yeah, so it's just simply order pair of the j function. So we have our formula. H prime is simply j of x. H prime of 4 is simply j of 4. J of 4 is equal to 0. Okay, next page. It's going to be the same stem, but we're just going to be asking more questions involving the stem. So let's go to the back page. Still the same piece of information that's given. But we're really able to just review a bunch of material from first semester just with this one FRQ problem. Okay, part E, on what interval is h increasing and concave down? Okay, so H. Okay. Now, from the previous page, what did we gather? We say that H prime is equal to J of X, right? So I want us to kind of keep that in mind here. We know that H prime so really, this is J of X, but this is really the what? The derivative graph of what? Of H, right? This is basically the H prime graph. So if you want, you can just call this the H prime graph. And it says, on what interval is the H increasing and concave down? Well, we're basically asking to interpret a derivative graph, right? So think about first semester, how do we interpret derivative graphs? We make our label, right? Anything above the x-axis indicates where our H graph is rising. Anything below the x-axis indicates where our H graph is decreasing. Anything on is going to be where my H graph is slope 0. Right? So let's create a slope sign line for H. My endpoints are from 0 to 6. Sorry, 0 to 6. And what critical points can I put onto my H graph? Yes, not quite 2. It's more 1.5 and 4. Okay, 1.5. So this is not the actual movement of the H graph. Okay, let's look at whether our graph is above or below. What's happening between 0 and 1.5? It's increasing. So the actual graph, this is not the actual graph, this is the derivative graph, but we know the actual graph is going to be rising on the interval from 0 to 1.5. Okay, what's happening between 1.5 and 4? Decreasing. What's happening between 4 and 6? Increasing. Okay, so let's just indicate what we know about this graph. We expect what at 1.5? Relative max. At 4, you expect a relative min. The graph is rising on the first interval, falling and rising, right? So the graph looks more like this, right? Not like this. It's going to have a different, slight. Obviously, your H graph is going to look different than your H prime graph. Okay, but we know this is going to be really helpful for us to determine what we want to answer. Okay, now let's create a second derivative graph, second derivative sign line. This is where we're looking for concavity and points of inflection. So if we're looking at the derivative graph, how do we pick out the points of inflection of the original graph? Peaks and valleys, right? Max and mins. So we have, how many points of inflections do we have on this H graph? 3. Yeah, 1 and 3 and 5. Okay, so 1, 3, and 5. Okay, now how do we determine concave up and concave down? We look at the what? The slope, right? So wherever my H prime graph is rising, that's where my actual graph is going to show a concave what? Concave up, right? Positive slope is concave up, negative slope is concave down. So concave up for the first interval, concave down for the second interval, concave up for the third interval, concave down for the fourth interval. So now it's easy because we have everything that we've already labeled. Okay. Where's the graph increasing and concave down? So we want both to occur at the same time. So concave up, sorry, yeah, increasing and concave down. So that's going to be between 1 and 1.5, right? Okay. So this interval here. Right. Increasing and concave down. Okay. Where else do you see increasing and concave down? Okay. From, yeah, 5 to 6. So increasing here, but yet also concave down. I should have maybe lined things up a little easier so we can kind of see it, but we want both to occur at the same time. Also, we can look at the graph and kind of tell as well. Increasing means it has to be above the x-axis, and concave down has to be a negative slope. So basically, if you look at this graph and say, okay, it's got to be above the graph and decreasing slope. So above the graph and decreasing slope, you can also tell by looking at this graph as well. I like to, create a slope sine line, concavity sine line, but you can also, if you know what you're looking for, you can also pull it from your graph. Yeah, let me write this. Yeah, have us write this down here. Sorry. Okay, the graph of H is increasing concave down on the intervals from 1 to 1.5 and then from 5 to 6. Oh, reason why is because H, yeah, H prime is greater than 0 and H double prime is less than 0. Yeah, I can say that. You can say, yeah, you can also say where H prime is positive and H double prime is negative. Yeah. All right, let's see if we can fit in one more part here, part F. Find the absolute min and absolute max on the interval from 0 to 6. So if we see this, what are we thinking here? This is an application of what? Absolute min, absolute max. That's not average value theorem. Extreme value theorem, right? Extreme value theorem, right? If I want to find absolute max, absolute min, extreme value theorem. So extreme value theorem says, what candidates are we looking at? We want to find out where we want to find critical points, yeah. And we want to test endpoints. All right. So we have H, we have this in front of us, so this is helpful, right? So what critical point do we want to involve? 1.5 and 4 and 0, 6. So basically, everything you need to find is from your H prime, right? Your H double prime is never going to be helpful because points of inflection is not going to be a critical point, right? Critical point is only going to come from relative max, relative min, and from your endpoints. So we only have to test 4 points: H of 0, H of 1.5, H of 4, and H of 6. And we have a formula that can help us find each of those points. Okay, so let's build these out here. So H of 0 is the definite integral from 6 to 0 of J of t. Okay. Again, I want to read the graph from left to right. So to make it easier, I can do what? Flip the bounce. So from 0 to 6, let me just make this a little bit faster for us. We know all these are triangles, 1/2 base times height. So this ends up being 0.75. This is a triangle, but we have to make sure we make this what? Negative, right? So negative 3.75. And we know that this is a positive 3. So from 0 to 6, I just add up all those numbers. But I need to make sure I put a negative in front of what I add up together. It ends up actually giving us 0. Okay, next up, H of 1.5. Again, we're stuck with that upper bound always being smaller because the 6 is below. So we always going to have to flip here. Okay, so from 1.5 to 6, negative 3.75 plus 3, but then I got to make sure I change the sign of that. Okay, two more here, h of, what's next? H of 4, yeah. Change the sign, flip the bounds, because I want to read from left to right. Okay, what's this equal to? The area from 4 to 6 is just 3, but then I need to make it what? Negative, okay. And the last one is easy. What? H of 6, my bounds are going to match, so that's just going to be equal to what? 0. Okay. Now, I don't really care about the location. I just want to find out what's the highest and lowest y values. What's the highest y value that you see? Yeah, that's the absolute max. What's the lowest y value that you see? -3. Okay. The location is not that important. What's more important is that you're actually identifying the y value. Okay. So absolute max is 0.75. Absolute minimum is -3. You don't have to indicate where it's located. Just tell me the y value. Okay. I hit you guys with a ton of stuff, but this is basically what your FRQ is going to look like. We'll have all day tomorrow to review, Thursday and Friday morning. Okay, so it's just going to be front and back of these concepts. Right, so your homework is pages 7 through 10. Yeah, so let me go to your calendar here. So tomorrow, pages 7 through 10. Okay. So I did most of 7 and 8. Yeah, so you guys did 9 and 10. I'll probably pick out some problems for us to review, and then we'll go to 11 through 14. Yeah, we'll do 11 and 12, and you guys do 13 and 14. Or I may just try to pick out problems from those 4 pages, and then you guys will finish whatever I don't do anything about it. All right, come get your phones. Okay, great. Thank you. Oh, you got number 1 as well?
Yes. So.
Yeah. Okay.
Let me just.